continue from the previous video, we introduced the bootstrap technique. So the bootstrap is the technique for simulating repeated random sampling. All we have is only one original sample. So please make sure this original sample is large enough and random. So that's why they can probably resample the population. Then according to this original sample, we will sample at random for many other resample. Why we can do that? Why the bootstrap works and why we need that? Remember, we have a parameter we want to understand in our population, but that's unknown. So one thing we can do is we do the large enough sampling for our population. Because the limited time and money, we only can have one random sample. But one random sample only can come out from the statistic for one estimation for the parameter in the population. We all know random sample draw by chance. So how we know this one estimation can well interpret the parameter from the population? We don't know because all the random sample, they have that difference and variety. So in order to get that, it's better we can have as many random sample as we want. But can we do that many times? We couldn't because we don't have that much money or the time limitation. But the bootstrap work is what? The bootstrap will create the many more sampling, but instead drawing from the population, we drawing from the original sample. Like we said earlier, your original sample need to be large enough and draw random from the population. So then according to this original sample, then we use the bootstrap technique to create many more resamples. So how to do that? The first thing, we have the same size. All the resample will be the same size as the original sample. For example, if this size 400. So then each resample, we still draw by random from this original sample. We draw 400 of that with the same sample size. In order not to have exactly the same sample as the resample, so then we need to draw with replacement. Right, so maybe they have a repeat data, but that's okay. That's all make the resample are random drawing. And also we know that the distribution for the resample will also pretty similar to our original sample. And we just say the original sample distribution will be similar to population. So these resamples, we can have as many we want. Each resample, they have their own statistic. For example, in our San Francisco city worker, from that population, we have that parameter for the median total compensation. So according to our sample, we have the statistic to find the median. The same thing for the real sample. Each one, they have their own median. They all have their median. Maybe they are 150, maybe 130, maybe 120. But that's all okay. After we get as many resamples data, then we get all their statistics. Then we can have a good range to describe the parameter from the population. So that's how our bootstrap works. We don't know the population, then we got the original sample, then we have many resamples. So in our demonstration, right, we do have the population information. The reason is we just want to demonstrate to show you the bootstrap technique will work. They can describe our parameter in the population with good range. So that's what we want to do in the demonstration. So just remember in our bootstrap principle, okay, so the resampling from the original random sample, they will be similar. Always remember this is similar to the sampling from the population with high probability. The reasonable for the estimation many parameter if the original random sample is large enough. So of course we need to require our original random sample is large enough by joined by random. Okay, so then we go back to see our demonstration. So remember that's our San Francisco city worker information. From this table, we try to get rid of some lower number so that we still have 37,000 data. So from this population, right, we do have the median on this total compensation median. But in real life, usually we don't have. On this demonstration, just want to show you our bootstrap technique work. Okay, so that's why here you will see here is the comparison we can have. Okay, so then, right, we need to create our sample, or our sample. So here we drove size 400 from the population that we get our sample. This one is in the video we talk, in the slide we talk about the original sample. So from this original sample, of course, we can calculate on the median for the total compensation. But the most important thing for here, we want to show you the bootstrap work, okay, the bootstrap technique. So once we have our bootstrap technique, remember we just have each resample from our original sample. So you don't have to provide any parameter because we use the same sample size and we do the replacement. So then each time you run that, of course, you can have your own resample data. But this resample data, the same thing we want to know. We have the distribution and also we can find the median. But the most important thing, we can do this many times. So that's why here we write our bootstrap median. From each time we do the resample, then we find the median. So if you run this function, it's every time you have one resample data. That's do many times. So that's why here we have repeat time. That's repeat 1,000 times. So every time we have our new median, resample median, we add to our array. Okay, so then we repeat 1,000 times. After we done the 1,000 times, of course, that's plot those 1,000 time resample into a histogram. Okay, so that's how here we create our table. Then we have our histogram. Okay, and also in this histogram, also that's put our population median here. So that's why you can compare the result. So that's why here is the histogram, the empirical distribution from the resample median data. So then from this distribution, yeah, we can see here, look pretty well because your population data actually kind of in the middle of the distribution. But how we can make this conclusion be more repeatable, we can use that. Like earlier we say, we have many resample. We are not on purpose to get only one number to describe the population. Instead, using this many resample data, we can provide a range to describe our estimation for our parameter in the population. So we will introduce the confidence interval. Because from that empirical distribution from the resample data, we want to provide a range we feel confident enough to interpret the parameter from the population. So we're using the 95% confidence interval. So this interval is the estimate of a parameter from the population. Of course, it's based on a random sample. The 95% we call confidence level. you can have your confidence level even start from 0 to 100. Of course, higher level of confidence will have wider confidence interval. The confidence is the process that creates the interval. It generates a good interval about 95% of the time. Also, that's the same thing. Remember, that's by chance. Also, 95% we are confident our estimation can good estimate the parameter. We can good interpret the parameter from the population. So back to our bootstrap result. Where is that 95% confidence interval? So that's here we say we need to find the confidence interval, right? So where it is, so then remember that's kind of how we calculate the p-value. Since we have the 95% confidence interval, and we just say they are kind of the distribution is symmetrically, right? So since you have 95% confidence interval, that means the rest of the 5% is what we want to looking for. So this 5% shared by the left side and the right side. So on the other hand, in the left tail area, we need to find that 2.5%. So then in the right side, on 2.5%, we need to find that. But instead, to find the area, actually remember we do have our percentile function. So this percentile function, you just need to give them the percentage, then give them the array of your data. So that's why here we have our bootstrap medians. Then we try to find where is that 2.5%. We call that left. So on the other hand, the other 97.5% will be the right. Okay, so after you got that, also then you can see here is our range. So in this range, we know the median from the population will be between 125,000 to 143,000 something. It do meet, right? It did meet what we have. You see here is our, this one is our population median. Okay, so that's why here we have the range. So when we do the interpretation, we give them a range. So then if the population parameter is in this range, that's a good estimation, right? Okay, so since we know the left and right, so if we want to put that in the histogram more clear, of course you also can plot that range. So here we have our left and right. So then we put the color yellow. So we replot our histogram. Okay, so then you can see that's our 95% range. So for this one, actually kind of nice, the result. So what will affect this 95% range? Yeah, of course, one more thing. If we have our random sample, but here remember the number on 125 to 143. Okay, so we can redo our bootstrap. Okay, so if you have the original, the same sample data, then we just redo our 1000 time resample. Okay, so the same thing, that's find the range. Okay, so then you will see, oh, that's still 125 and 142. Earlier it's 143. Okay, so you can see if you run again. Okay, you run again. Okay, yeah, they are kind of in this similar range, right? So that's all we can see here. If your original sample data don't change, so then your resample, they will be very similar in the similar range for your output. But what will change if we make our sample data different? So on the other hand, you see here, that's draw another 400 sample. Okay, so then you will see here, you do the bootstrap 100 times. Yeah, then your left and right has a little difference. Okay, so that's the bootstrap. We will continue to talk about that again in the lecture 24, but we'll stop here. So for you, you can also change to try more bootstrap testing to see the 95% confidence interval, and also check if you change your original sample, how that will affect your 95% range, 95% interval. So I will stop here.